Welcome to this section. We're going to be looking at support vector machines. So this is the second section in our course, and it's the second machine learning model for your toolkit. The support vector machine was ultimately the state of the art before some years ago deep learning waded onto the scene. And what we want to do is review it, see why it was the state of the art, what it's used for, how it's used, and how it can be used to explain AI models, which is of sort of critical importance in this day and age. Understanding how machine learning models work without having to know every mathematical detail, very useful. So let's look at some of the objectives coming up in this course. First of all, we want to understand a cutting edge ML technique. This is something that I would certainly use on typical problems. It's a fast to use algorithm, it's flexible, it's robust. It's definitely one that you should be applying to your data sets in the right scenario, which we'll look into. Then using support vector machines to explain AI. So by AI, I'm talking about machine learning models, really. In fact, I'm talking about this model. And if this model, as a black box, starts churning out predictions, we want to ask ourselves, well, what was the decision? If we've got a classifier, why have you classified this, let's say, diagnosis, this medical diagnosis, into serious rather than not serious? And the way that support vector machines handle that is by offering support vectors. These are very natural byproducts of the mathematical technique, and they provide two things. Number one, sparsification of the solution. The support vectors are just a small subset of all of your data, but they're the only ones needed going forward to draw inference with the algorithm. Okay, so you have a huge data set, and this technique trims that data set right down, so the compute is far shorter. Really important. But also, those support vectors are by definition the closest to affecting the decision, and so this means you can inspect those specific data points with expert opinion, and then these will give you some insight into how the machine learning model is understanding your problem. Very important objective to get your head around. Then we'll expand our toolkit, not just with classification models, but also with regression models. Okay, so you can set up a support vector machine as a regressor, and we'll look into the mathematics on how you execute that. Not just that, but you can set up support vector machines with the kernel trick. Yes, we're bringing back my favorite subject from the last section back into section 2. So I hope you're paying attention, because now we're going to be able to extend this algorithm in much the same way as we did with the linear regressor model. Then we'll be implementing support vector machines with scikit-learn, a very good implementation, very fast, and we'll inspect some of the attributes, some of the parameters that need to go into this model using scikit-learn, and of course we'll be flexing the machine learning algorithm on real world data. So that's all very exciting, but let's just take a step back now and think once again, what's the trick? What's the support vector machine? What are we trying to do? Why do we like it? Well, ultimately, in a support vector classifier, we'll get onto regression, or in a classification problem per se, I've drawn one here. I've tried to draw some blue blobs and some yellow blobs, and the task for the machine learning model is, given the x-axis and the y-axis, can you draw me a function which separates blue from yellow? And yes, it can. It draws a diagonal line down the middle. What differentiates a support vector machine is that it tries to maximize the margin between those lines. So you have the line, you have the margin around it, and it pushes those green lines, the margin lines, away from each other as far as possible. That's in the objective function built into it. Technicalities of the support vector machine are that occasionally, when I say occasionally, I essentially mean always, you'll have noisy data. You're not going to have this distinct classification problem, otherwise life would be too easy. So then you have to allow for some of those data points to become misclassified, or even just lying inside the margin. And this is where the support vector machine really comes into effect, because it gives you hyperparameters to control that degree of penalization of data points crossing the margin, crossing the decision boundary and becoming misclassified. A really powerful machine learning tool. And then just to expand a bit on what I said about support vectors, they are the vectors closest, or either on the edge or inside that margin. Okay. Once you've got these vectors identified, then they're all you need to build the model going forward. So in this graph, we've plotted the contours of a support vector classifier. That is given any point on that grid. These are this is the side it's going to be on if it's going to be classified blue or gold, and the degree to which it's classified in that sense. And in a pink ring, we've circled the support vectors. Okay, so you can see them. Now, when I say we can apply the kernel trick, here we've solved a linear classification problem with a line. Well, what if we wanted to use a nonlinear classifier? Enter the kernel trick. And what do we have? We have a method by which we can seek nonlinear representations of the features. Remember those from last time? And we can perhaps gain more insight into the best fitting classifier for this model. In this case, the model has learnt to find a more sort of circular shape around each cluster of data points. And notice also that the support vectors are no longer sitting on a strip in the middle. Many of them are, but some of them are around the outside. And these are the crucial vectors needed to go on with the classification. So, really exciting topic. Looking forward to pulling apart all the details. Let's just go through what exactly is going to be coming up. So first of all, we're going to look into some of the theory behind just maximizing the decision margin, what the decision margin is, how you write it down. And then we'll construct ourselves a support vector machine, and in particular, a support vector machine to solve classification problems. We'll then inspect the concept of having noisy data and how we go about rectifying that with a support vector machine. And then we'll be deploying kernels into our support vector machine to generate an essentially completely state-of-the-art machine learning model. That's what you'll be putting into your toolkit. And then finally, if you have a regression problem, we'll extend the method for regression. And then, of course, we'll go through different code examples. We'll look through graphical code examples, as well as real-life data examples in the wild to see how a support vector machine can handle these just typical problems. So, I suppose all I've got to say now is please support vector machines.